Hello everyone. Welcome to the Electronics with Bill channel. And I thought you do a couple of YouTube videos here to see how this works. I'm a retired engineer, worked a long time in electronics. And also then I also taught electronics at University of Texas Arlington for several years. And I'm not doing that right now, so I'm going to try a couple of YouTube videos. Maybe we can show people how things work, some things work, and show people what engineers do for a living, maybe a little bit. So for the first video, I wanted to do one that I had as a supplemental video from my electronics class. It's about a GM alternator, SI Series Alternator. Basically, what is an alternator? Um, you know, what kind of stuff's inside it, some of the parts inside an alternator, what does it look like, the magnetics, basically how does a three-phase AC machine work, the rectifier, three-phase AC rectifier, the regulator, internal regulation that regulates the output of the alternator. So we can talk about all of that in this video. And there is some math. It's not a math video, but there is some math. There's a mention of a calculus operation called differentiation, which the derivative in calculus, where you calculate the slope of a function or the rate of change of a function. And there's a mention of if you differentiate sine omega t, you get omega cosine omega t, basically. And that's about the extent of the calculus involved. And omega, some of you may have an issue with or may not, is a velocity variable usually used for angular velocity, which would have units of radians per second in many cases. So, for example, if you had revolutions per minute of 6,000, let's say, that would be, of course, 100 revolutions per second, which would be 2 pi times 100 radians per second. Okay, so that would be 628 radians per second, which would correspond to 6,000 RPM. And that would be a radian is 57 degrees if you want to just for comparison to things people may have more experience with. So on that note, let's get started with the video.
Hey students, this is a optional automotive video. Covers alternator. That's the module that provides the electric power in the car, and what charges the battery, and then the schematic of this alternator, how it works, and the regulator. Okay, and here's a picture of the alternator, and there's a picture here of the alternator, and then this is a cutaway view showing the pulley on the end, the shaft, the slip rings that conduct electric power to the rotor here. Rotor is just an electromagnet, and the power for the electromagnet comes through these slip rings. The brushes that rub on the slip rings, so that this can rotate and still maintain connection with the power source for the electromagnet. And the stator here, which is where the coils are that extract the AC power from this machine. The rectifier is down here, and the regulators up here against the back wall of the alternator, and then there's a fan right here that pulls air out of the front of the alternator and it rushes in through the back, so it cools the rectifier bridge and the regulator here on its way through. Okay, so that's kind of a real quick overview of the mechanical layout of this alternator. And this is a SI GM. It's a GM alternator. And by the way, this book here is a shop manual. It's an automotive shop manual, factory service manual, if you would. Okay, and here's the schematic provided by GM for this alternator. It's kind of showing the alternator and how it's wired into the car. So this big dash line here surrounds the alternator itself, and then within this big dash box is this box, which is the alternator. Okay, now you can count components here. I counted 12 diodes, 1, 2, 3, 4 resistors, 5 resistors, 2 transistors, so 1 capacitor, maybe 2 capacitors. I think you can say that that the diode is definitely the most the component that has the largest number in this in this alternator. All right. In terms of the interface to the vehicle, the battery terminal here. This is the output. This is this particular car has a 108 amp alternator. That's where the 108 amps comes out right there, out that battery terminal, and that's this stud right here that sticks out the back. That's where this wire attaches. And then these other two inputs to the alternator. One is for the idiot light. That's the generator light when it tells you that your alternator is not working if it fails. That connects here. And then this is the sense lead. And the regulator needs to know what the system voltage is, and it regulates. This is the lead that it looks at to regulate the output. You notice that they don't regulate the actual alternator output. They regulate the voltage on this lead here, which can connect someplace else. They call that remote sensing. Okay, these two terminals are the sense lead and the idiot light lead connect here to these two tabs. There's like a low power connector that plugs in into that into those two, that connects to those two tabs. So that kind of like a big overview here of what goes on in an alternator. And I'll pause this for just a minute. Okay, picking back up, I'm going to talk just for maybe 5 minutes about how does alternator work? How does it make power? And so here is a very simplified picture that might give you an idea how an alternator can work. And so this little square here is supposed to represent the rotor, the rotating electromagnet. And then these two coils here represent the coils that are in the stator, the fixed part of the alternator, the part that doesn't turn. And then the field excitation here drives the slip rings. And the way the battery is drawn here with its positive side here, current would go through the rotor like this. And using our right hand rule, where you let your fingers wrap around in the direction of the current, your thumb points in the direction of the magnetic field, and your thumb would be pointed up. And so the magnetic field lines will flow from bottom to top with north up. Okay, the North Pole up. Not that really matters, but that's just the for this particular polarity of the field excitation and the current going in this direction around the rotor, the magnetic field that's generated will be with north in the up direction. Now you notice that for this particular orientation right here of the rotor relative to the stator, there would be no magnetic flux coupling into the coils on the stator. So our flux would be 0 as shown, magnetic flux. Now suppose I rotate this 90 degrees counterclockwise. So now north would be facing to the left, north would be facing in this direction, and then I would have magnetic flux coupling through this coil, and then through this is some kind of a magnetic material here, presumably iron. That's a good magnetic flux conductor. And then, so the magnetic flux flows through here, coupling all three of these turns that are shown there, and then flows through the frame of the stator, back around to this side, and then couples through these three coils, and then back through the rotor again. Now that's with the rotor turned at 90 degrees from where it's shown the way it's shown here. Now, if I rotate it another 90 degrees, then I have the same picture I have here. Only thing is, north is down and south is up. All right. Now if I rotate it yet another 90 degrees, then I have north pointed to the right, and then I would have magnetic flux. Instead of going this way, it goes this way. It couples through these three turns, and goes through the stator frame, and then comes back around through these three turns, and then back to the rotor again. So if I was to plot flux on this axis versus theta, it might look like this. So this is theta, or angle, in other words. This is angle, theta, and then this is flux, magnetic flux. Usually use this Greek letter phi, I think, V, phi. It might look like this, where we start out at zero flux, then we increase in a positive direction, so to speak. So if we call this positive flux, then this would be negative flux, and we might have something like this. All right. Now we can let theta equal omega t, if you would, and omega t looks like this. If you plot omega t versus t, this is theta. If theta equal omega t, it looks like this, where we have a slope that depends on omega. All right, and then so this would be possibly sine theta. So phi is proportional to the phi is equal to some constant times sine of theta, or some constant times sine of omega t. K is a constant here. Now, Faraday's law says that to get a voltage around the loop, we don't have a magnetic flux. We have a change of magnetic flux. So the voltage around any loop is proportional to the change, the rate of change of the magnetic flux. And so if our magnetic flux looks like this, then our voltage around any given loop here, now this would be one loop, like one turn on this coil right here would be one loop. The voltage then is proportional to some other constant, K2, if you would, times the rate of change of the flux. But if the flux is K sine omega t, the rate of change of that flux is K omega cosine omega t. Again, here's our flux, K, some constant times sine omega t. Our voltage is some other constant times K omega cosine omega t, because the derivative of sine is a cosine. So, obviously, one of the constants that we have to deal with here is if we have a voltage per turn, well, we got 6 turns shown here. Well, we obviously have 6 times as much voltage as what we have per loop, because we got 6 loops there. And how strong this flux is, how strong this flux up here is, one of the things that goes in this K is how strong is this magnetic field. So that flux is proportional to what kind of current we had flowing in the rotor here. And then you notice another factor here is this omega that comes out in front when we take the derivative. So because the voltage induced is proportional to the rate of change of flux, omega, the rate of rotation, directly affects our voltage. So in these constants here of proportionality, there are factors like how much rotor current do you have, how many turns do you have on the rotor. That certainly determines the magnetic flux. And then how many turns do you have on the stator? What's the rotation rate? The air gap between the rotor and the stator, because air isn't as good of a magnetic quote conductor unquote as iron is. So the bigger the air gap, the less output you get, less voltage you get. So you can see here maybe that first of all you get AC, and the reason you get AC is because our flux looks like this, and then when we differentiate this, we get that. All right, and the output's proportional to omega, directly proportional to speed. Now, you know car engines run over a huge range of speed, so RPM-wise, from maybe 600 to 6,000 RPM, it's a factor of 10 at least in RPM, and then directly proportional to the current that flows in the rotor here. So some people a long time ago figured out that to control the output of a generator or AC alternator like this, you can control this rotor current, and then that would allow you to control the output of the machine. And you certainly need to, because it operates over a huge range of RPM, and also, not only that, a huge range of load. The amount of current the alternator needs to put out can vary from maybe 10 amps to 100 amps pretty easily, just under different operating conditions. So that is just a little quick tutorial on what the heck is an alternator, and they call it an alternator because it makes AC, and the AC output would appear across these two terminals. And by the way, these two coils are in series. So next, I need to talk about three-phase AC, because this would be just a single-phase AC right here. And if we wanted a single-phase generator that would make sinusoidal AC, you could have something like this, only this is a very simplified version of it. So I'm going to pause this video again. I'm going to change pictures here. Okay, back again. Here's a picture from a different source showing how the coils might be arranged, and I say might be arranged in inside the frame of a AC machine like this, a three-phase AC machine. Now here, the two coils that we talked about previously in the previous picture, which I'll put back up, this picture here, this coil and this coil might be represented by this coil and this coil. And then you notice that there are two more, quote, phases here. There's this coil and this coil, and there's this coil and this coil. And those, this coil and this coil are connected in series, as we show here. This coil and this coil are. Likewise, this coil and this coil are connected in series, and this coil and this coil are connected in series. And so we have three generators really here, making three phases of AC at the same frequency. And why are they different phases? Well, they're displaced 120 degrees from each other around the perimeter of the frame of the stator. So I guess that's about all there is to say there. You notice, like, if this is, let's say this is north and this is south, then when this north passes by, this is the rotor here, and this turns, either clockwise or counterclockwise, the flux builds up, the flux couples through this coil here, flows through the stator frame, then through this coil, and then back into the south side, all right? And then when the rotor has rotated 180 degrees, then the flux travels the other direction, first through this coil, and then around this way back to the south through this coil. But that happens in all of these six coils here, just they're 120 degrees out of phase with each other because of their different displacements around the perimeter of the stator frame. And these three phases, there's six coils here. Phase one, that's this one and this one, are wired in series. Phase two, that'd be this one and this one, that's like this. And then phase three is this one and this one, that's this. And they're connected like this in what they call the delta configuration. Now, this is a standard AC power term, and power company people use this terminology, and there's no reason you need to worry about that. But they call it delta configuration because this looks like the Greek letter delta. There's another configuration called the Y, which kind of looks like this, so they call it WYE. It looks like a Y, but they spell it out, WYE. That's another configuration for AC power. This is the delta configuration. And why do I show that? Well, because this particular alternator has the three-phase AC configured as in the delta configuration. That's why I mentioned that. It's three-phase AC, in the delta configuration in this particular alternator. And again, these coils are in the stator, and this is the rotor, and then the stator coils are like right here and right removed from the frame of the alternator. So you see all of there's the magnetic kind of a base for the stator, the frame of the stator, and then the coils are inserted in slots in the stator, and then okay, here's a picture of the rotor too, which might be interesting to you. And there's a slip wrench. Okay, so that is. I'm going to pause the video again, and I'm going to get another picture. Okay, so we're back. Here's a picture. Shows, again, very simplified. If we have a single stator coil and a single electromagnet magnet rotating, this would be our single phase AC output. Here is a picture of the 3 phases produced by a 3-phase machine. Again, I have 3 coils spaced 120 degrees around the perimeter of the frame, and then one electromagnetic rotating, and then I get 3 sinusoidal outputs that are 120 degrees displaced in phase from each other, and these phase A, B, and C corresponding to coils A, B, and C. Now finally, it's getting time to talk about what do we do with all this fine stuff. So, one more picture, another picture yet. Here is the picture of the alternator. I mean, this is a schematic of the alternator. This is the same thing that's in the shop manual, but I just redrew it. You notice we got 3-phase AC, and we pick off these 3 phases, and we come over here to these 6 diodes. Now, these 6 diodes are the power rectifiers. So this ground here is to the case on the alternator, and then this is the output, the plus output that connects to the battery. This is a big high power output right here. So how does this work? Well, I want you to notice that at any given time, there's always one phase that has the maximum magnitude. Now, for instance, right here, at this point right here, phase A has a larger magnitude than either phase B or phase C do. Right here, phase B has a larger magnitude than either phase A or phase C do. Right here, phase C has a larger magnitude than either phase A or B do. So at some point in time, each phase has the maximum magnitude, be it either positive or negative, and it doesn't matter. It doesn't matter. We'll see why in just a second. So now let's look back to our rectifier schematic. So whichever phase, let's suppose at a particular time, phase 1 has the maximum magnitude with, let's say, this being positive and this being negative. All right, so what diodes turn on here? Well, this diode turns on, current going this direction, and then we need to get back to this other side from ground, so that turns on this diode. So if phase 1 is maximum magnitude with plus and minus as shown, then we turn on this diode and this diode. How about if phase 1 is maximum magnitude with the reverse polarity? So that's like this, then this is plus and this is minus. So now we need to turn on this diode to have current flow to the load, and then to get back to here, we need to turn on this diode. So if phase 1 is maximum magnitude with sign as shown, we turn on this diode and this diode. Okay, so you can see that all 6 of these diodes turn on. They turn on 2 at a time. These diodes turn on 2 at a time, but different ones at different times, and so they kind of strobe. If the diode was lit up when they were on, they kind of strobe back and forth like this as the rotor turns. So that is how the rectifier works. 6 diodes. 6 diodes required. 2 of them turn on at a time, so we lose 1.4 volts for diode drop if you use standard silicon diodes. Now, why do we do this? Well, there's a huge reason why we do this, and if you think about it, so looking back at this picture again, think about what our full wave single phase rectifier output looks like. The full wave single phase rectifier output looks like this, with the bottom flipped up, right? So the full wave single phase rectifier output looks like this. The full wave 3-phase rectifier output looks like this, where this is 0 here, and this is 0 here. It's almost DC without even filtering. And we only depend on phase A from here to here, roughly. And then next, what would be next? Next goes to phase C from here to here. See, so it doesn't. The output doesn't drop to 0 like the single phase full wave rectifier does. It stays high. So this is much easier to filter or not even filter at all. And by the way, you can put a load on this, and that doesn't make the ripple worse, like it does if you try to use a capacitor input filter, like we learned, with a full wave bridge. The more the load you put on it, the worse the ripple is. That's not true for this. So that hopefully explains what they're doing, why they use the full wave, the 3-phase full wave rectifier in an alternator. Now, what about? I want to try to at least cover all these diodes, what they're all for here. We got these 3 diodes. What the heck are they for? Well, they're the exciter supply. All of this stuff, including the rotor, needs power from something. And these 3 diodes tap off the same AC that goes to power the battery, this plus terminal here. This is just kind of like a parallel rectifier here that makes power for the exciter supply. So if you think about it, this diode and this diode, these 3 diodes share these lower 3 diodes here. You don't need to reduplicate. I mean, you don't need to have 6 diodes over here for the exciter supply, because you can use these diodes for both purposes. These diodes serve for both. These lower diodes here, these 3 lower diodes, serve both as part of the rectification for the main high power output for the alternator, and as well, these 3 diodes work with these 3 diodes to make the exciter supply. Now, why do we have a separate supply for the exciter? Why don't we just take, use this output for the exciter? Well, the reason is that when you turn the engine off, you don't want your battery discharging through all this stuff over here. Because what's the voltage regulator going to try to do when you shut the engine off? If you shut the engine off, the battery voltage drops, and the voltage regulator is going to turn on the current to the rotor, trying to bring the battery voltage back up, which of course can't happen because the engine's not running. So it just runs the battery down pretty quick. This rotor current is about 3.5 amps. It can be up to 3.5 amps when it's running wide open, and so you don't want to leave your alternator, drawing 3.5 amps off your battery. You run it down pretty darn quick. So they use a separate supply right here, so that this is powered only when the alternator is functioning. You don't have to worry about having it discharge your battery when you're not using the car. By the way, the idiot light, the generator light, also connects to this terminal right here. And so the generator light connects to the ignition switch, so that when the ignition is on, the generator light will light if the alternator is not working. But as soon as the exciter supply comes up, then both sides of the generator light are connected to battery, and the generator light goes out. That's how the generator light functions. Now, one side of the generator light connects here, the other side connects to the ignition switch, so that when the ignition's on, if the engine's not running, you have current coming through the generator light down through this circuitry here in the exciter circuit, in the regulator, to ground. And then as soon as the alternator starts working, and when you start the engine up, then this potential comes up, the battery potential, and the generator light goes out. So that's how that works. Now, one other thing, the sense. You notice here's the sense line to the regulator, comes in here. The alternator does not sense its output. There's a separate sense line that the auto designer gets to connect up where he wants. This is what they call remote sense. And by the way, when I say sense, I mean this is the line that the regulator looks at, so that it knows whether the output of the alternator is too high or too low. And so reason why this remote sense is a strong plus is this is a 100+ amp alternator right here, and so you could have a fair amount of drop in this connection right here, and you might lose a half a volt before you ever get over to the battery, for instance, just in the wire that runs from this node over to the battery. And so this remote sense allows you not to have to worry about that. So you can regulate the battery voltage, and then if this voltage needs to be a little bit higher than the battery voltage to make that happen because of the drop in the wire, that's okay. So that's why they do remote sense. So that said, So how does this circuit work now? The regulator circuit. You notice we have our exciter power supply here, and here's the rotor, and there's the slip rings that feed the rotor. And so you can see that if this is at 14.5 volts, let's say, because the alternator is working, then current can flow through the rotor if this transistor is turned on, TR1 here. And TR1 is biased with a resistor here, R1, off of the 14.5 volts. So current can flow down through here, like this, and through the emitter base junction of TR1, and turn TR1 on, and then TR1 passes current through the rotor. Now, if this transistor TR2 was not here, I would hope that this would allow TR1 to turn on enough to run the alternator wide open. All right, so in other words, I don't know what value this resistor is because they don't tell you in the schematic, but I would hope that whatever this base current is here to this TR1, it's a power transistor, whatever the base current is in here, multiplied by the beta of this transistor, that would be enough collector current to run this alternator wide open. Because that's what needs to happen when the alternator runs wide open. This device is off when the alternator output is low, and so this resistor then turns on this transistor here, and so now what is the current that flows? You can figure that out fairly easy. If this is 14.5 volts, because that's what the alternator should be regulating to, is about 14.5. If this is 14.5 volts, this potential here is 1.4 volts at room temperature. How do I get 1.4 volts? We've got a VBE for this part, that's 0.7, plus a diode drop here, which is 0.7 volts. Talk a little later about what this diode's for. So this is going to be 1.4 volts at room temperature. So the drop across this resistor is 14.5 on this side, 1.4 here. 14.5 minus 1.4 divided by R1 is the base current to TR1. Hopefully, that base current times the beta of this device, at least 100, let's say, would be more than enough to handle the 3.5 amp rotor current to make to allow this transistor to come pretty close to saturating, because that's what has to happen when the alternator runs wide open. This resistor biases up TR1, turns it on, and allows current to flow through the rotor here to ground through TR1. Now, what about TR2? What do we have TR2 here for? TR2 is how the alternator regulates. Now, we have V-sense over here. V-sense, when V-sense gets too high, current comes down through here and turns on TR2. And when TR2 turns on, it steals the base current that would go to TR1. Instead of going to TR1, it goes through TR2 to ground, and then TR2 can shut off TR1. TR1 shuts off, the alternator shuts off. So that's kind of how it works. Now, what voltage does that happen at? Well, it happens at VBE for TR2 plus this Zener here. There's a Zener diode. There's a real application of a Zener diode. So VBE plus VZ for the Zener, whatever that is. And I believe this is a 6.2 volt Zener. So plus minus 6.2. It doesn't say that on the schematic, but on the internet I found some place that said it was a 6.2 volt Zener. And then this voltage divide ratio right here. So the equation for turn on, or for turn on of TR2, in other words, where TR2 starts to turn on and steal base current from TR1, is when V sense times R3 over R2 plus R3, and I'm lumping these two resistors together as R2. One of them is a thermistor, which is a temperature sensitive resistor. Okay, so these two together I'm calling R2, parallel combination. And then this is R3. So that's a voltage divider. This voltage divider here. So V sense, this voltage, times this voltage divide ratio, minus VZ, which is 6.2, minus VBE equals 0. At that point, at this V sense, the alternator will turn on TR2. And when TR2 turns on, we start to cut off TR1. We start to steal base current from TR1, throttle it back, so to speak. So, you can, I don't know what these resistors are. They don't tell you, so I can't calculate that. But let's say R2 was roughly equal to R3. Let's say. if that was the case. And this voltage divider here would be a 2-to-1 voltage divider. So if I had 14.5 volts here, I'd have 7.25 volts here, in other words. So in that case, you could see that it's probably about what it is, because 0.7 plus 6.2 is 6.9, and then 6.9 times 2 would be 13.8 volts. That would then be where you would predict this circuit would start regulating if this was a 2-to-1 divider here, would be at 13.8 volts at room temperature. Again, 0.7 plus 6.2 is that's a 6.2 volt zener. That's 6.9 volts. And then what do you have to have here to get 6.9 volts here? Well, if it's a 2-to-1 voltage divider, you need 13.8 volts here. So that is how this regulator works, kinda, because we can't really calculate because I don't have values here. All right, that's where it starts to work, where it starts regulating. And now it's a very beta dependent design, and I don't really like it because it's beta dependent. But I did want to show you. There's a couple other diodes here. Here's a Zener diode. We talked about those in class. Here is D1, which is for level shifting purposes. It requires that you need now, instead of needing 0.7 volts to turn on TR1, I now need 1.4 volts here at room temperature to turn on TR1. That makes it easier to shut off. It makes it easier for TR2 to shut off TR1. Now, why would that be an issue? Here's why. When you're hot, remember, this VDE for TR1 is going to be down 0.55 volt when you're hot. And the beta is going to be high. It's going to be hard for TR2 to shut off TR1. In other words, to steal all of its base current, because TR1 is starting to get kind of close to saturation when its collector gets down to 0.55 volt. So by putting this diode in here, this transistor will start to shut off when this node is at, even hot, 1.1 volts. 0.55 for this, plus 0.55 for that. So this transistor does not turn on until this node gets up to 1.1 volts, even hot, and that allows this guy's gain is improved, and I believe I read someplace they had a little issue with this transistor not being able to shut this guy off when it was hot, and that's why they put this diode in. All right, just for level shifting purposes. It's not used as a rectifier. It's not used for protection. It's just for level shifting. It just changes the voltage at which that needs to be here to turn on this transistor. It raises it up a little bit, makes this device work a little bit better. Okay, one last diode I wanted to point out. Here is one of those, I think they call them flywheel diodes. You notice it's right across the slip rings which feed the rotor. This diode is there for protection. Protects this transistor. If this transistor, some transient happens over here on the sense line, for instance, and this alternator tries to shut off the rotor current real quick. Now, this rotor is a pretty big inductor, and you try to shut off its current, and it's going to give you back a huge transient. So this is a diode that allows the rotor current to continue to flow so it doesn't destroy this device. Consider, again, in normal operation, I have current flowing like this. If I shut this device off really quick, if I try to take it out of the picture, I'll put my finger over it so like it's gone. That current is not going to stop instantly. You know, one way or another, that current is not going to stop instantly. And so this way, it is allowed to kind of gracefully decline, continue flowing through D3 there until the resistance in the rotor and the 0.7 volt drop of the D3 there absorb the energy that was stored in the rotor, and then it saves TR1 from getting blown up. So that is how I'd like to talk about the gain of this a little bit, but this video is already way too long, and so I'm not going to talk about the gain of it. But it's very beta dependent. You notice there's not a whole lot of resistors here that set gains, so it's temperature sensitive and device sensitive from a gain perspective, and it's not the best design in that regard. But man, there are millions of them out there. This thing is one of the most prolific circuits ever. Millions of them. GM cars from like early 70s to almost up to 2000. By the way, modern alternators, this is modern alternators in cars, they don't even have self-contained regulators anymore. They use the ECM to control the alternator, and they have a data bus that goes out to the alternator, and the micro the ECM, the electronic control module, tells the alternator what to do. So this is a self-contained regulator that where the alternator has its own brain, so to speak, and it controls its output. But modern cars, they don't do it this way anymore. At least some of the modern cars don't, and so I'm not sure that's even necessarily all that good. But this was a very, very heavily used circuit over a whole lot of years. So anyway, I think that's going to be it for this video. So we'll talk to you in class. Uh,
Well, video's over. I hope you're able to get something out of it. Now I want to make a comment. This is an old alternator design, probably older than many of the viewers, and so you might wonder whether that is relevant or not. And I can absolutely promise you that the principles are the same in a modern alternator. Laws of physics haven't changed at all. The magnetics, the rectification, and the principles of the regulation, i.e. adjusting the field or the rotor current, would be the same. Now, the exact mechanics of how that regulation works could be a little different with some of the more modern alternators. Sometimes the ECM, electronic control module in the car, could be involved in adjusting the regulator, the rotor current based on the system voltage. And sometimes some manufacturers do that or have done that. And another thing that I have seen that a little bit different was that rather than trying to vary the current to the rotor in a linear fashion using a pass device, as the current could be adjusted by adjusting the duty cycle of an on-off type waveform. And that is also something that could be done, which would save a little power dissipation in the pass device. But the principles are the same. Now, I just wanted to mention something that wasn't stated in the video, and that's why is the alternator temperature compensated? And in the video, there was a thermistor in parallel with R2, and that would make the regulator's voltage it regulates to a function of temperature. And I just wanted to mention why that is. And the reason why that is because a lead acid battery will not take a charge at 14 volts when it's very cold. So you have to raise the voltage to get it to charge. Now, why would you care about that? Well, for short trip driving, if you don't drive a long way, you may not replace the energy that you use to start the car during the time you have it running. So it's considered a good idea to, when the battery is very cold, to raise the voltage a little bit, and then you don't want to leave that voltage high when on a hot day or when everything warms up. Then you'll cook the battery, and that there's not much that'll shorten a battery's life more than overheating it or overcharging it. So you don't really want to do that. So that is the reason for the temperature compensation. Now, you could argue easily that it might have been better to measure the battery temperature rather than the temperature of the regulator in the alternator. And indeed, some auto manufacturers do that. They'll actually have a temperature sensor monitoring the battery temperature, because that's the reason why we temp comp the alternator output is for the benefit of the battery. And so measuring the temperature of the alternator is not really maybe the best thing to do. So anyway, that is just a little addendum to the video, which, and I hope you were able to get something out of it. And I wanted to thank you for watching, and appreciate all comments. positive or negative.